We previously learned that intermolecular forces can determine a substance's physical properties. Now that we've discussed some of the basic intermolecular forces, we can talk about a few physical properties of liquids: viscosity, surface tension, vapor pressure, and boiling point. We will relate each of these four physical properties back to their intermolecular forces. Viscosity describes a liquid's resistance to flow. The stronger the intermolecular forces are within a molecule, the higher the viscosity will be. For example, if we compare honey to water, honey has a much higher viscosity and will resist flow much more than water would. Honey has a very, very high amount of sugar or sucrose within it. Sucrose is made up of two units that are combined together. One is glucose and one is fructose, and these two units are combined through something called the glycosidic linkage. If we look at the molecular structure of sucrose, there are many locations where hydrogen bonding can take place. We learned that hydrogen bonding is one of the stronger intermolecular forces. And since there are so many locations for different hydrogen bonds to form, this molecule has rather strong intermolecular forces, which cause it to be a very viscous liquid. So the link between IMFs and viscosity are that as intermolecular forces increase, the viscosity of a liquid will increase. There is a direct relationship between the two. Surface tension is the ability of a liquid to form a thick molecular layer on its surface. If you've ever seen a bug walking on the surface of water, this can happen because water will be able to form a strong surface tension. Molecules that are in the middle of the sample have intermolecular forces forming between them all around them. So for example, this water molecule in the center can form different intermolecular forces with all of the surrounding water molecules because it's in the interior of the sample. Versus a water molecule on the surface layer. The ones on the surface can only form intermolecular forces between the molecules on the surface with it and right below it. Therefore, they overcompensate and form stronger bonds at the surface of the molecule, which forms the thick layer that we see for various liquids. The trend between surface tension and intermolecular forces are, as intermolecular forces between the molecules get stronger, the surface tension of the liquid will increase as well. So stronger intermolecular forces equal a higher surface tension. Those two are directly related to one another. Which of the following substances is the most viscous liquid? In order to answer this, we first need to determine which intermolecular forces are present amongst the molecules. A is water, and in water we can see that there is an OH bond present. Therefore, it will have hydrogen bonding. In B, we have methanol, and there is also an OH bond present, so this will also have hydrogen bonding. C is ethylene glycol. We have some hydrogen bonds present. And in D, this is ethanol, and in ethanol there is a hydrogen bond present as well. So since all four molecules contain the same strongest intermolecular force, there has to be a way that we can distinguish between them. In water, there's not only one hydrogen bond present, but there's actually two hydrogen bonds present per molecule. In B, methanol, there's only one hydrogen bond present per molecule. In C, ethylene glycol, there is also two hydrogen bonds present per molecule. And in D, ethanol, there is only one hydrogen bond present per molecule. So in terms of which one is going to be the most viscous, we learned that viscosity increases as the strength of the intermolecular forces increase. So we're looking for the molecule with the strongest intermolecular forces. Therefore, for now we can cross off B and we can cross off D because in methanol and ethanol, there's only one hydrogen bond per molecule. So now between molecule A, which is water, and C, which is ethylene glycol. Hydrogen bonding is the strongest intermolecular force present in both molecules, but they both also contain London dispersion forces. London dispersion forces are present in all molecules, polar and nonpolar. Since ethylene glycol is a bigger molecule and has more electrons in it, it's going to have the stronger London dispersion forces compared to water, which will have the weaker London dispersion forces. London dispersion forces will be the thing that tips the scale in favor of ethylene glycol being the one with the strongest intermolecular forces overall. Therefore, C is going to be our most viscous liquid. One of the most important physical properties of liquids is their tendency to undergo a change of state from liquid to gas. This process is called evaporation. Everybody has seen evaporation. If you've had a glass of water on a hot summer day sit outside, and over time the level of the water gets lower as liquid molecules are changing to gaseous molecules. To understand evaporation, we need to understand the motion of molecules. As you know by now, molecules do not stand still in liquids. They bounce around against their neighbors. If a molecule near the surface of the liquid can gain enough kinetic energy, it can escape the liquid state and make a transition from the liquid state to the gaseous state. This is what happens when liquid water turns into gaseous water. If one of the molecules at the surface is moving fast enough, it can escape the attractions or the intermolecular forces of its neighbors and enter the vapor state. Evaporation and vapor pressure of a liquid are closely related. Evaporation, we learned, is an open system where the liquid molecules gain enough kinetic energy that when they become a gaseous molecule, they can escape. Vapor pressure of a liquid we can imagine taking place in a closed system. So now let's pretend instead of an open glass, we have a closed glass. An equilibrium will develop between molecules in the gaseous state in the closed container and molecules that are in the liquid state. We use double arrows to show that equilibrium. If we measure the pressure of the gas that's in the headspace of the closed container, this would represent the vapor pressure of that liquid. When equilibrium conditions are established, the rate of molecules in the liquid phase gaining enough kinetic energy to evaporate and go to the gaseous phase will equal the rate of gas particles colliding with the liquid surface and condensing. This rate of evaporation equaling the rate of condensation is known as a dynamic equilibrium. Essentially, the effects of condensation and evaporation will cancel each other out. There is no apparent change at this point. The number of vapor molecules will remain constant, as will the number of liquid molecules. It is considered a dynamic equilibrium because the activity has not ceased. Molecules will continue to evaporate and condense. They will just do so at equal rates. When a liquid evaporates, the molecules that enter the vapor exert a pressure called the vapor pressure. This vapor pressure is the equilibrium pressure of a vapor above its liquid in a closed container. We learned that in a closed container, a dynamic equilibrium will be reached between the gaseous state and the liquid state. Bromine is a great example because liquid bromine has a dark red color, and we can actually see its gas particles sitting above its liquid particles. Those gas particles will exert a pressure in that container. It's much easier for molecules within a liquid to break away and escape their liquid state to the gaseous state if the intermolecular forces between those molecules are weak. Therefore, the vapor pressure will increase with decreasing strength of intermolecular forces. So as intermolecular forces become weaker, vapor pressure of a liquid will increase. And vice versa. With stronger intermolecular forces present, the vapor pressure of that liquid will go down because the molecules will be held tightly together and it will be harder for them to break away to their gaseous state. We can compare the structure of water and isopropyl alcohol. Water and isopropyl alcohol both have hydrogen bonding. Water has 2 hydrogen bonds per molecule, whereas isopropyl alcohol only has 1 hydrogen bond. They both also have London dispersion forces. But hydrogen bonding is the strongest intermolecular force present, and therefore the fact that water has 2 hydrogen bonds will make its overall intermolecular forces stronger than isopropyl alcohol. The vapor pressure of water at room temperature is about 24 torr, whereas the vapor pressure of isopropyl alcohol is 44 torr. Water with its stronger intermolecular forces has a lower vapor pressure. It's harder for it to evaporate and make the transition from liquid state to gaseous state than it is for isopropyl alcohol, which has weaker intermolecular forces than water. The rate of evaporation is influenced by temperature. You've seen that hot water will evaporate faster than cold water, so it should be no surprise that vapor pressure is also influenced by temperature. As the temperature of a liquid increases, the pressure above the liquid will also increase. Recall that temperature is a measure of the average kinetic energy. As the temperature goes up, the kinetic energy of the particles will go up, making it easier for them to make the escape from the liquid state to the gaseous state. Therefore, the temperature increase will cause the vapor pressure to be higher. The temperature will increase and the vapor pressure will increase until a liquid reaches its boiling point. Which of the following liquids has the highest vapor pressure at room temperature? Recall that as vapor pressure goes up, the intermolecular forces go down. A molecule that has weaker intermolecular forces between it will have a greater vapor pressure because the molecules will be able to escape the liquid phase more easily. So we want to determine which intermolecular forces are present amongst A, B, C, and D. A is water. Water contains hydrogen bonding, which is a rather strong intermolecular force. It has 2 hydrogen bonds per molecule. B is methanol. It contains 1 hydrogen bond per molecule. C is a compound known as an ether. Its name is dimethyl ether, and it does not contain any hydrogen bonding, but the molecule is a polar molecule, so its strongest intermolecular forces are going to be dipole-dipole interactions because it's polarity. And D is ethanol, and it also contains 1 hydrogen bond per molecule. Since A, B, and D all contain hydrogen bonding, they have stronger intermolecular forces. C contains only dipole-dipole interactions. Therefore, out of the group, it will have the weakest IMFs. Having the weakest intermolecular forces means that it's going to have the strongest or highest vapor pressure. If you were asked to check whether a pot of water was boiling, what would you look for? The answer is bubbles. When a liquid boils, large bubbles will form at many places on the inner surface of the container and rise to the top. If you were to place a thermometer into the boiling water, you would find that the temperature remains constant, regardless of how you adjust the flame below the pot. A hotter flame will just make the water bubble faster, but it doesn't raise the temperature. Any pure liquid remains at a constant temperature while it is boiling, a temperature that is called the liquid's boiling point. We previously saw that during evaporation, molecules that were at the surface of the liquid had enough kinetic energy to escape and make a transition from the liquid state to the gaseous state. But when something is boiling, molecules throughout the entire sample of the liquid have enough kinetic energy to vaporize. When a liquid reaches its boiling point and bubbles are forming, those bubbles contain the vapor of the liquid that is boiling. For example, when water boils, those bubbles contain water vapor or steam, not air. If you are boiling alcohol, the alcohols will contain alcohol vapor. The boiling point of a liquid is highly dependent upon the external atmospheric pressure, and boiling point will change depending upon what the atmospheric pressure is. Those bubbles of vapor cannot even form until the liquid temperature of the water rises to a point at which the vapor pressure equals the atmospheric pressure. This is known as the boiling point, the temperature at which the vapor pressure of the liquid equals the external atmospheric pressure. This is why water would boil at a lower temperature somewhere like Denver, Colorado, than it would in New York City, because the atmospheric pressure is lower in Denver and the water doesn't have to be heated to as high of a temperature to make its vapor pressure equal the atmospheric pressure. As the boiling point of a liquid increases, the strength of the intermolecular forces between the molecules are stronger as well. Molecules that have stronger intermolecular forces will require more energy to break them apart and get them to go from the liquid phase to the gaseous phase. Therefore, the boiling point will increase. To make it possible to compare the boiling points of different liquids, chemists have chosen 1 atmosphere as the reference pressure. The boiling point of a liquid at 1 atm is referred to as its normal boiling point. When we look up boiling points in reference sources, they're often listed if the pressure is at 760 torr or 1 atmosphere. The boiling point will change though depending upon what the real external atmospheric pressure is for the day. The following graph shows as the temperature goes up, the vapor pressure of water, ethanol, and diethyl ether will increase until they reach their boiling point. The normal boiling point would be the temperature at which it's boiling at 760 torr. We can also use boiling point data to assess the strength of the intermolecular forces. Water has a relatively high boiling point at 100 degrees Celsius. Water, we learned, contains 2 hydrogen bonds per molecule. Ethanol boils at 78.5 degrees Celsius, and it has 1 hydrogen bond per molecule. Diethyl ether boils at a much lower temperature, 34.5 degrees Celsius, and it does not contain any hydrogen bonding. It only contains dipole-dipole interactions. Weaker intermolecular forces will cause that liquid to boil at a much lower temperature. Stronger intermolecular forces will cause the liquid to need much more energy to break the intermolecular forces of attraction and cause it to boil at a higher temperature. Which of the following will have the lowest vapor pressure, and which of the following will have the lowest boiling point? The molecule with the lowest vapor pressure is going to be the one that has the strongest intermolecular forces of attraction. There's an inverse relationship between the two. On the other hand, the molecule with the lowest boiling point is going to be the one with the weakest intermolecular forces of attraction. So first we need to determine which IMFs are present in each of the 4 molecules: 2-methylpropane, 2-propanone, ethanol, and water. 2-methylpropane is a hydrocarbon made up of only carbon and hydrogen. It has no polarity to it. It's a nonpolar molecule. Therefore, the only intermolecular forces to consider are London dispersion forces. 2-propanone contains a carbon-oxygen double bond. That carbon-oxygen double bond is going to be polar. Oxygen will be slightly more electronegative than carbon, therefore the oxygen will develop a partial negative charge and the carbon will develop a partial positive charge. It doesn't have any hydrogen bonding though, so its strongest intermolecular forces will be dipole-dipole interactions. Water has 2 OH bonds, therefore it contains hydrogen bonding, 2 per molecule. And ethanol contains 1 OH bond, so it has 1 hydrogen bond per molecule. The one with the lowest vapor pressure will be the one with the strongest intermolecular forces, which in this case would be water with its 2 hydrogen bonds per molecule. The one with the lowest boiling point is going to be the one with the weakest intermolecular forces. In this case, it would be the 2-methylpropane, which is a hydrocarbon that only contains London dispersion forces. The following chart shows vapor pressure data and boiling point data for the 4 molecules that we just looked at on the previous slide: 2-methylpropane, 2-propanone, ethanol, and water. Water, we can see, has the highest boiling point of the four, which we predicted based upon its 2 hydrogen bonds per molecule. The boiling point increases as the strength of the intermolecular forces increases. And if we choose 25 degrees Celsius, or what's known as room temperature, to compare the vapor pressures of the 4 molecules, we can see that the 2-methylpropane has the highest vapor pressure, and the water with its strongest IMFs has the lowest vapor pressure. There's an inverse relationship between vapor pressure and strength of intermolecular forces. Which of these compounds has the highest normal boiling point? Let's draw their Lewis structures. CH3F. Carbon is the central atom and there's 4 things around it. It's going to be tetrahedral, but since all 4 things are not identical, it's going to be a polar molecule. In B, we have CH3OH. We're going to have carbon with 3 hydrogens and 1 OH bond. This is also going to be a polar molecule. CH2F2, carbon with 2 hydrogens and 2 fluorines. This will also be a polar molecule. And lastly, CF4, carbon bonded to 4 fluorines. It's tetrahedral and symmetrical since all outer atoms are fluorine. Therefore, this is going to be a non-polar molecule. Now let's think about what types of intermolecular forces are going to be present in each of these molecules. A, we have a polar molecule, therefore it's going to experience dipole-dipole interactions. The carbon will be partially positive. The 1 outer fluorine will be partially negative. In B, we have methanol. We have 1 OH bond per molecule, so the strongest IMFs will be hydrogen bonding. In this case, the oxygen is partially negative. The hydrogen is partially positive. Also, the carbon bonded to the oxygen will be partially positive. In C, CH2F2, we have 2 polar CF bonds. Carbon will be partially positive, and each fluorine will be partially negative. No hydrogen bonding, but since it's polar, there'll be dipole-dipole interactions. And in CF4, since the overall molecule is nonpolar, the strongest IMFs present will be London dispersion forces. Since we're trying to answer which molecule would have the highest normal boiling point, boiling points increase as the strength of the intermolecular forces increase. So since methanol contains hydrogen bonding, this one is going to have the highest boiling point. Methanol has a boiling point of 65 degrees Celsius, and all the trends we saw with our other molecules, whether they were polar or nonpolar and what intermolecular forces they had, will show up in their boiling points as well. CF4, which was D, had only London dispersion forces, so this should have the lowest boiling point of them all. And CF4's boiling point is negative 128 degrees Celsius. And A is a little bit polar, and C is a little bit more polar than that, even though they both contain dipole-dipole. So A has a boiling point of negative 78 degrees Celsius, whereas C has a boiling point of negative 52 degrees Celsius. So its intermolecular forces are a little bit stronger than A because there's 2 polar carbon-fluorine bonds within C.